Rust is an upcoming programming language. It's been very popular, but one of the challenges is, especially in our embedded space, is how can I use something that has the level of commercial support that is going to provide me with something that I can use for a long-term project? AdaCore has been working with Rust for quite some time now. Why does Rust need a commercial compiler like the one you're providing?
Well, Bill, let's unpack a bit what you mean when you say commercial compiler. So first, a subtle distinction. I think we should really be talking about tool chains rather than just talking about compilers. Because while the compiler is an essential component of the tool chain, there's several other components that are just as necessary. If you look at Rust, for example, you have Cargo, which does crate management and build orchestration. At the other end, you also have the linker. This is actually putting all the pieces together and giving you your final product. So these are also really important, even if they're not as immediately obvious. And this distinction becomes even more important when we talk about certification a little bit later. So what makes a commercial tool chain? Now, at a minimum, I would say a commercial tool chain requires three things. First, stability, which comes from building and verifying the tool chain using a rigorous, reproducible, and industrial process. The second component is security, especially now as there's so much concern about security, so much concern about software supply chain security. You need to have tools delivered with, for example, a software bill of materials. And third, professional support. And what this really means at its heart is that you have support that includes a service level agreement so that you can be confident if you get stuck, you can become unstuck and you know by when. So ultimately, once they reach a certain scale or a certain level of investment or commitments, we feel like commercial software developers really need to have commercial tools. And once they reach this point, there's only really two options. The first is to stand up an internal team to provide all of these elements that I ascribe to a commercial tool chain. Or second, to buy the commercial tool chain from a third party. And the reality is that only the very largest companies can or will commit to standing up an internal team. The amount of resources that's required to do this has to be amortized over a very large number of developers. Most companies don't hit this economy of scale, even if they're large. So the reality is that for most serious commercial software developers, buying commercial tool chains becomes a necessity. There's another aspect to this. The growing emphasis on software supply chain security means that simply bringing up a new tool chain, like Rust, can be prohibitively expensive for developers who must show compliance to regulations. So, for example, anyone who's working in aerospace and defense probably is going to have to turn to a third party and purchase a commercially supported tool chain. They're not going to be able to do this on their own. And then the last comment I have here is that many sectors within the high integrity community are subject to certification requirements, even apart from security. So if we think about commercial aerospace or medical or rail or automotive, these are just a few industries that have certification requirements. And so developers who are working in these domains are going to need to have a clear path to certification before they commit to adopting a new language or pick a tool chain. And due to the cost and complexity of achieving certification, only tool chains that are backed by commercial entities are ever going to be able to provide the necessary support for certification. So I would say Rust absolutely needs a commercial tool chain, and this is going to enable it to be used at scale for high integrity applications.
So what does AdaCore provide with this Rust solution?
Well, at a high level, we provide stability, security, professional support, and a clear path to certification. But if I drill down and get a bit more technical, there's two components that I'll highlight. The first is on the toolchain side. So at official launch later this year, we're going to provide at least three things: Cargo, which is Rust Package Manager and Build System, Rust C, the compiler, and GDB, the debugger. We're also nailing down supporting tools that will be available at launch. Probably we're going to include Clippy, which is a linter for Rust, and Rust Analyzer, which is a plugin for Visual Studio Code that provides IDE support for Rust. Now, right now, we're in our early access phase, and we're engaging with customers to define precisely what should be in this initial offering. But GNAT Pro for Rust is completely compatible with the upstream toolchain. What that means is that customers who can use open source tools will be able to supplement the offering in GNAT Pro for Rust with open source tools. Over the next couple of years, we're going to expand the toolchain rapidly, and ultimately, we're going to provide the high integrity community with a complete commercial toolchain for Rust. But there's a nice incremental approach that's available because of the upstream capabilities. That's the toolchain side. The other component of this is the platform side. So GNAT Pro for Rust allows users to target relevant, high integrity embedded platforms, many of which aren't available in the upstream. So for example, at launch, we'll support Wind River's VxWorks. We'll allow customers to target both DKM, kernel modules, and RTP, user space modules. We'll also support LST's Lynx OS 178, and we're always talking with customers to identify what do they need, what platforms do they really want to see supported, so we can put that into our roadmap. Our vision is to achieve an OS platform support matrix for us that's similar to our support matrix for Ada, C, and C++. We also have customers who want custom ports. So many of the major aerospace and defense companies have in-house real-time operating systems that they've developed, and they would like to see Rust support on their platforms. AdaCore has already ported its Ada, C, and C++ toolchains to many of these custom operating systems. And so we're prepared to work with customers to do that for Rust as well. So that's what we provide with GNAT Pro for Rust.
Now, I've actually played with this and been working with Rust. I found almost no difference between the tools that I was using on open source and what you had provided me to test. What does AdaCore provide with respect to the open source platform? Are there differences? Are there similarities? At this point, I think it's almost one for one in terms of similarities.
Right now, it's meant to be one for one. So right now, you're meant to be able to use GNAT Pro for Rust as a drop-in replacement for the upstream tools. What we're doing is we're taking the upstream tools, we're stabilizing them on a particular selected version, one version per year, and we're building that in our infrastructure in a fully reproducible way, generating the evidence that we need to show a software bill of materials, and running the full battery of test cases in an extremely rigorous, extremely reproducible way. So we can then turn around and provide that tool chain, that artifact to our customers with the backing of our software service level agreement, so our customers have complete confidence they have what they need. This also means as we explore platform support, we're fixing bugs in upstream as we find them, and we're going to be turning those fixes around to the community so that we give back in that way. Today, there's no significant difference between what we're offering and what the community offers from the perspective of how the technology works. What we're giving customers is this guarantee that what we've given them is the right thing with the software bill of materials, and that we're fully prepared to support it.
Well, that obviously leads into certification. Why is that important? I think you've touched on it a little bit, but in terms of what you're providing, how is that going to make things easier?
Developers of certifiable software need, first and foremost, a commercial toolchain. This is because certifiable software is long-lived. In some sense, this is by virtue of the cost of achieving it in the first place, but also by virtue of the domains in which you find certifiable software. So for aerospace and defense, for example, these systems typically last for decades. And the tool chain needs to be there from development through operation all the way until obsolescence of the platform. Developers of certifiable software also need a clear path to achieving their certification objectives. No one wants to embark on a software project that needs certification without assurance that they're going to be able to comply with the objectives in their standard before they even start writing a line of code. Now, these details depend on the certification domain, but broadly, there's three components that we need to talk about. We need to have a qualifiable toolchain, we need to have certifiable runtime libraries, and we need to have qualifiable support tools. So you might have heard last year about Ferrocene, a compiler targeting a subset of the Rust language that achieved qualification under ISO 26262. Now, AdaCore participated in the qualification of Ferrocene. in the development of the Ferrocene specification language, and the technical work producing qualification evidence, and in the preparation of the qualification documents. Ferrocene is a great accomplishment, but as we talked about earlier, the compiler is just one component of the toolchain, and developers of certifiable software need a qualifiable toolchain. For Rust, that means looking at the linker and probably also looking at cargo. And ultimately, our experience is that developers are going to want a qualified compiler that targets most or all of the Rust language. So AdaCore will leverage its experience working on Ferrocene and leverage the work the Rust Foundation is doing on the development of a Rust language specification to qualify the Rust compiler and then ultimately qualify a Rust toolchain. That's the toolchain. But as I said, that's just the start. Languages like Rust also depend on runtime libraries to do a lot of their heavy lifting. So even a Rust no-std target typically depends on several libraries like libcore and liballoc. So we're going to leverage our experience with certification to certify Rust runtime libraries, starting with libcore, liballoc, libproc macro, and then ultimately turning to certify most or all of libstd. If we don't do it, then certifiable software developers are going to have to do it themselves. And nobody wants to pay the cost of certifying the runtime when they could otherwise buy it from a third party. Finally, certification standards typically include objectives that imply tool support. So coverage is a great example of this. Most standards require some degree of coverage analysis, and that implies a testing tool that can generate coverage data. But that testing tool has to be qualified before its outputs can be used as evidence for the certification. So that qualification has to be accomplished for that tool. Other tools also often need qualification. For example, tools that report on software complexity metrics. Here again, AdaCore is going to leverage its experience with the development and qualification of supporting tools to help ensure that developers' needs are met.
Where do you think Rust is headed with respect to the embedded space, where certification oftentimes is a requirement?
The White House released a technical report entitled Back to Building Blocks, A Path Towards Secure and Measurable Software. And a key conclusion of that report is that we must stop using unsafe languages, specifically C and C++, and move aggressively to adopt memory-safe languages. Now, as an aside, I'd be remiss in not pointing out that Ada is also a memory-safe language, and Ada has been around for a long time. To a certain extent, it has an advantage over Rust because of its pedigree. It's been out there for 40 years. So I'd say to programmers who are looking for memory-safe languages, if you don't find what you need for Rust, you should definitely take a look at Ada. But Rust is a memory-safe language, and Rust is appropriate for systems and embedded programming, and Rust is a top 10 language in terms of popularity. So when I look at Rust and I look at the embedded space, I see enormous potential for Rust here. What I think is we just need to help remove barriers to adoption, and that's what we're trying to accomplish with GNAT Pro for Rust. We want to make it as easy as possible for software developers who want to work in this space, who have requirements that they need to comply with, to be able to pick up a commercially supported toolchain that will let them get their work done.
One of the things that I've played with in the past with AdaCore's tools is a programming language called Spark, but it's not really its own programming language, is it? And why is that important to our discussion about memory-safe programming languages?
So Spark is a language that's based on Ada. So it takes all of the foundations that Ada provides, and then it introduces as minimal restrictions as we can possibly get away with to ensure provability. That's the fundamental goal with Spark, to help users get into a position where they can start proving that their code complies with contracts that they've written. So Spark is a fantastic language. And one of the things that we've done with Spark is we have actually built upon Ada's default memory safety and made it better. So Ada's memory safety is largely, although not entirely, it's largely enforced at runtime through runtime checks. When those checks fail, an exception is raised and either the program is halted or the exception is handled. Spark takes this a step further and it leverages the ownership model that was introduced by Rust and layers that on top of Ada. So if you use Spark, you effectively get the kind of ownership that you have in Rust applied to Ada, thus making the memory safety guarantees that Ada gives you statically enforceable as opposed to being dynamically enforceable. That's the first really cool thing that Spark does. The second really cool thing that Spark does is it allows you to prove properties about your program. And this is a capability that goes a step beyond what's currently possible with Rust today. Could we in the future imagine Rust that has the kind of provability that we have in Ada? Yes. There are, in fact, researchers who are looking at that, who are looking at extending the kind of formal methods that we have in Spark to Rust. But here, Ada has a significant advantage over Rust. Ada has a type system that gives you the ability to talk precisely about subtypes for your numeric types. So for example, you can put ranges on integers and say some particular integer valued variable is only allowed to go from 5 to 10. And these kinds of restrictions on your variable ranges make it much, much easier in Spark to complete your proofs. It's quite probable that Rust would need to add these kinds of features to the language, either through supplemental annotations or direct changes to the language itself, before it would be able to achieve the level that we can reach with Spark. So today, AdaCore's position is, if you want to use Rust, absolutely use Rust. It's a great language. We will support you. You will get memory safety, and you will get statically verifiable memory safety for all of your code that's not marked unsafe in Rust, all of your safe Rust code. Wonderful language to use. You should use it. But if you want to go that step further, if you want to go to proven correctness for your software, then you should really be looking at Spark. And one of the things that we're trying to do with GNAT Pro for Rust is explore interoperability between Ada, Spark, and Rust. At launch, we'll give you GPR builds with the ability to interface with Cargo so that you can bring Rust code into your Ada programs. And over the course of the next several years, we're going to be exploring advanced binding modes between Spark and Rust so that both languages can take advantage of the ownership model that the other provides and offer really tight and really natural integration. So that's something we're working on. Stay tuned.
Well, thank you very much, Tony, for introducing us into AdaCore's Rust support. Thank you.